Hello everyone, welcome to lecture 27. This is part 2 of lecture 27. So today we will continue this avalanche studies. So this is just to make the continuity. So on the basis of the characteristics of the snowpack, avalanche problems are characterized, right? From that the potential and behavior of avalanche can be understood, and we have seen that there are 4 different types of problems. So, the first one is the character, then we have size, location and then likelihood, and we were discussing about these avalanche problems one by one. So, to see that character, to start with, we will see this particular video and you will be able to understand what exactly we mean by character, right. So, just see the loose weight, wind slab, storm slab, glide and so on. These are the different types of character for avalanche and particularly snow avalanche, right. So, the first one is the storm slab, release of a soft cohesive layer which is a slab of new snow that breaks within the storm snow or at the interface between new and the old snow, right. So, if this is the new snow and this is the old snow, this is the position, right. Then comes the wind slab, release of a cohesive layer of snow formed by the wind drifted snow, right. So, here you can see the example and this is for the storm slab. Then comes the wet slab. So, the name itself is wet, so you will be able to understand, release of a cohesive layer of snow caused by melt water weakening the bond between the slab and an underlying weak layer. So, you can see that weak layer, this has been detached from the main mass because of the wet slab, right. Then comes the loose wet, release of unconsolidated damp or wet snow. So, here you can see these are very small scale, right. Then comes the cornice, the release of an overhanging mass of snow formed by wind deposits, right. So, here you can see the cornices, and the glide, release of entire snow cover as a result of gliding over the ground. So, it is because of the precipitation, because this precipitation will bring temperature to this ice mass, right. And if there is a surface which is having high melt water content, then this entire mass will slide like this one. Then the persistent slabs, release of a cohesive layer of snow when the bond to an underlying persistent weak layer breaks. So, here you can see this layer. Deep persistent slab, release of a thick cohesive layer of hard snow, a slab when the bond breaks between the slab and an underlying persistent weak layer deep in the snowpack or near the ground. So, here you can see this is the deep persistent slab. Then comes the loose dry, release of dry unconsolidated snow. So, here you can see the examples. Dry loose avalanche can act as a trigger for slab avalanche for the bigger scale, right. Dry loose avalanche are the simplest problem to manage because of their predictable behavior and relatively smaller size. So, these are manageable and it will not cause any loss of life and property. Now, we can see the different types of avalanches here. So, dry loose snow avalanche, which is here, you can see the example. Then comes the wet snow or wet loose avalanche. So, this is the 2. Then powder avalanche. So, here it is 3. These are different types of avalanches, right. Then we have slab avalanche. So, here you can see this is the example of slab avalanche. Then gliding avalanche. So, this is the one, right. So, now comes the location, how it is important, right. So, you see this video, here the location will be highlighted. So, here you can see the north, south, east, west have been marked, and then we have to relate it with the topography, how they appear. So, slowly this video will explain how the locations are important and the directions are important, right. So, here now comes the topography. So, in the topography you can see the direction has been matched, right, both the direction, you can see these. Now, you can see this side is basically your eastern side, all these hills, there we have the eastern side. Now comes the location, the slope, aspect and elevation, how they play a significant role or critical role here. So, avalanche release generally requires a slope angle greater than 30 degree. The curvature and aspect of the slope also influence the size of the release area, right. The steeper the slope, the more dangerous it is. So, because of the steepness, you will have the higher velocity that can be achieved by the avalanche. The north facing slopes, these are very important. The fact that most accident occurs on north facing slopes could be because settling takes longer due to the reduced exposure to sunlight and because more weak layers form. Powder snow also lasts longer on the north facing slopes, which generally means that they are frequented more often. However, there are situations in which south facing slopes are more dangerous than north facing slopes, right. So, the south facing slopes are more dangerous. So, here you can see in this side it is more dangerous than the north facing slopes. Now comes the likelihood. So, you will be able to understand here how this particular hill is susceptible to avalanche. So, whether it is highly susceptible, whether it is less susceptible, or it is very certain that it is going to happen, that we can describe using the likelihood. So, the size, that also plays a major role here. You can see this is a relatively small size. When it is a large one or the biggest one, that will have more impact on the downstream area, right. And it has been observed that after avalanche, post avalanche, there is a flash flood condition in the downstream. So, the factors responsible for the avalanche are the higher temperature, seismic activities and movement or vibration produced by machines and explosives, that we have seen some of the areas that there we are using the artificial vibration to clear the avalanches, right. So, when we talk about the higher temperature, because of the high temperature, the surface layer of the snow packs melt, the accumulated snow will become highly susceptible to sliding down. Then comes the seismic activities. It is one of the important factors that leads to trigger the layers of accumulated snowpack, because earthquake generated seismic waves that cause the ground to vibrate, and that will trigger the avalanche activities. Then the vibration during the development activities, the terrain vehicles in regions with unstable layers of snow can dislodge the layers from the surface and cause them to slide down under the influence of gravity. Then we have heavy snowfall. So, when a higher rate of snowfall occurs leading to the snow accumulation on the mountain slope, it triggers the weaker layer of snow in the snowpack of unstable areas of the mountain, causing an avalanche. Now, we have wind direction. The direction of the wind determines the pattern of the snowfall as well as snow accumulation on the mountain slope. If the strong wind blows, then the upward direction of the winds might trigger the steep slope, which cause an avalanche. And the deforestation, we all know the plants or the vegetation helps to restore the area. Also, it reduces the intensity and frequency of the hazards. So, the tree and plants always protect land against natural disaster like flood, tidal waves, strong winds and also avalanches. So, if we see the avalanche hazard triangle, so it refers to the three key elements: snowpack, terrain and weather, right. and the weather, terrain and snowpack, they have different impacts and they can be studied together to find the avalanche hazard in a given area, right. So, continuing the factor responsible for the avalanches. So, layering of snow, it also helps to trigger the gradual snowfall creates layer by layer accumulation of snow that hypersensitive the snowpack. If something catastrophic event happened, then these layers of snow falls down that leads to avalanches, and the steeper slope are more responsible for such event. An avalanche is also caused by the influence of gravity. If gradual snowfall accumulated on the slope of the mountain, then it prone to rush down the slope at greater speed. Then the winter sports activity, that also can trigger, and we have seen some of the example in the previous part of this lecture, and there I showed you some of the videos where because of the skiing the avalanche was triggered. So, the avalanche conditions refers to the interplay between the factors like weather and snowpack. Snowpack can consist of multiple layers of snow, each one form a different snowfall that becomes compacted under the weight of the subsequent layer that lie on top, right. Then comes the weather, we have wind, temperature, snowfall and rain. Together they can impact and trigger the avalanche activities. So, the weather and snowpacks are very important. So, let us try to understand the recipe of avalanche. So, the snowflakes generally have 6 arms formed by the accumulation of weather molecules, 2 hydrogen and 1 oxygen atom. Sometimes the snowflakes stay separate, creating a weak pillow layer. If another hard layer is forced on the top of the snowpack, the millions of snowflakes within them have set the stage for one of the most deadly phases on earth. We have got a strong layer, then a little weaker layer and then another strong layer on top of it. They are more faster than other snowflakes, which can create a continuous hard layer of snow that can stretch across entire mountain slide. So, here you might have seen this particular video and it explains how this accumulate and how it triggers and then what is the resultant of a avalanche. So, when we talk about the weather, it plays crucial role here. So, the precipitation creates and influences the snowpack over the course of the winter. A new snow layer often poorly bonds with the old snow layer. Therefore, avalanche possibility typically increases during or shortly after snowfall. Rains also constitutes an additional load and warm and soak the snowpack. During a period of precipitation, the amount of new snow, the temperature and the wind are main factors for the development of an avalanche. An unfavorable combination of these factors leads to what is called critical new snow depth, and avalanche danger level can be expected to increase. Here you can see that lee side, right, and this is the windward side, right. So, in the lee side it will be more active. So, the wind is said to be the architect of avalanche. The wind is responsible for the formation of snow slab. The slab can only slide away if it is on the top of a weak layer, then only it will slide. These are also known as wind slab, are predominantly found on untouched lee aspect of the steep slope behind terrain breaks. So, this side, right. The temperature influences the snowpack, the transformation processes within it, and in particular the top 30 to 50 centimeter of the snow layer. Cold and warm air both influences the snowpack. Cold air leads to grainy, non-cohesive layer that when later covered in snow can become weak layer. Heat initially leads to settling. but can also destabilize if the snow starts to melt and soak the snowpack. So, we have an example from Uttarakhand. From March onwards, the temperature was higher than in previous years. So, the melting started early and the snow became wet. The liquid water content also increased, and because of the fresh snowfall over this wet snow, it will result in an avalanche. So, you see here, this is the area what I was talking about. Critical amount of new snow, that is also very important. So, the critical amount of new snow refers to how much new snow accumulates, which signals a considerable rise in the risk of an avalanche. During new snowfall, the wind generates drifted snow, which leads to enormous brittle snow slab. Low temperatures slowed the process of new snow sintering with the existing snow surfaces. So, here you can see the unfavorable condition and the favorable condition which are listed. Then comes the rain. As we all know, the rain also bring temperature to the snow, and then the snow can be wet snow, and slowly that will lead to the avalanche. For instance, it adds a lots of heat to the snowpack, which makes it unstable. Second, it adds mass also, so it increases the load. Rain causes the top area of the snowpack to become heavier, perhaps overstressing the weak layer beneath, right, and that will lead to the avalanche. Avalanche occurrence is dependent on both static and dynamic conditions. Favorable terrain condition for avalanche occurrence are example of a static characteristic. Terrain conditions that remain constant over time are known as static condition. Avalanche occurrence requires favorable terrain circumstances, otherwise favorable dynamic parameter conditions are irrelevant. So, here you can see the ground cover, land use land cover, and the digital elevation model has been used. From digital elevation model, slope, aspect, curvature and the elevation information has been extracted, and same time you have the land use land cover, and together they are going into the AHP, and then from the field we are getting the information to validate, and then we can go for the potential avalanche formation zone mapping. This example is from the Rishikesh valley. So, in the western Himalayas, the Rishikesh catchment is composed of an area of about 690 square kilometer. There are several large valleys and hanging glaciers such as Changban, Hanuman, Trishul, Bartha-Toli, Ronti glaciers. These are present, right. The region falls in the category of rugged topography with elevation ranging from 1200 to 7800 MASL, right. The catchment is enclosed by 8 peaks, with Nanda Devi being the second highest peak, rising to about 7846 MASL. The region is prone to avalanche due to the presence of hanging glaciers, as slopes are sufficiently steep, leading to ice calving from the terminus of the glacier. And we had a incident in past. You might have heard about the Chamoli disaster. It was because of the ice wedge detachment, right, and it was here in the location. I will share the details now. So, this is the position of the detached wedge, right. So, it was on 7th February 2021 that a major rock mass and glacier ice dissociated from the northern slope of Trishul mountain, resulting in an avalanche, and the velocity was ranging in the downstream around 127 to 134 miles per hour, right. And the studies revealed that the 60 million metric ton that mass was crashed over the Ronti, and here out of 60 million metric ton, 80% was rock and 20% was the metamorphosed ice. So, here you can see the same area we have studied using the physical prototype of this triangular wedge, and then subsequently we have used the satellite images, and then we have studied the reason behind this rock ice wedge failure. So, this is the methodology that we have adopted in this particular work. So, we use the Sentinel-1 GRD data, then we also had input from the field investigation, and then optical satellite data set and the digital elevation models were used. The Sentinel-1 GRD data, that was used to measure the or estimate the glacier mobility. However, the digital elevation model and the field information like rock type, slope, wedge geometry, right. So, that was used for the probabilistic analysis of the slope. Also, we have done the rockfall simulation, and then subsequently we have concluded that this particular rock ice wedge failure was not because of the glacier mobility, because the glacier was moving at a very constant rate and there was no abnormality that we have seen. So, here you can see the list of data set that have been used in this particular study, and for the glacier mobility we have used the sub-pixel intensity offset tracking, and that was used to measure the velocity, and based on that we have got that for this given area the maximum mobility, that is 5.84 meter per year, was observed, right. And for this mobility we have also studied all along the glaciers and with different position in the glacier, right, and then we tried to study whether it was consistent throughout the glacier or whether it was varying at different location. So, maximum annual surface displacement is seen towards the end of the glacier flanks, ranging between 150 to 185 centimeter, which reduced to less than 10 centimeter near the snout, right. It is to be noted that the superficial displacement of the Ronthi glacier body is comparatively less than the other glacier bodies such as Trishul and Bharti in Rishikesh Valley. Minimum surface displacement registered by satellite is in the post monsoon period and maximum displacement is observed in the pre-monsoon period. Then we have also studied the Annapurna mountain range avalanche, because this is one of the very popular reason where we experience the avalanche very frequently. So, the incident occurred at an altitude of around 3230 meters, close to the base camp of Annapurna, one of the highest peak in the Himalayas, right. So, using the satellite images and this particular adopted methodology, we have tried to map the avalanches in Annapurna region, and here you can see all the glaciers are marked with this particular color and combination. So, the avalanche activation zone, the possible reason behind such pattern can be attributed to the backscattered response due to sloping mountain surface lying underneath the snowpack, right. So, here you can see the backscattering intensity that has been calculated. As the topographic gradient of these regions are comparatively higher, greater than 30 degree, freshly precipitated dry snow can undergo easily sliding than the other areas. This leads to less deposition of dry snow, giving dominance of backscatter response from the underlying ground surfaces. So, here you can see the temporal classification of avalanches. So, here we have identified the different locations which are having the avalanche activity. So, red color is used to mark the recent avalanches and the old avalanches can be seen with blue color, and the unsure region it is in the white color. So, in Indian Himalayas, the Indian Army and DRDO have jointly installed the avalanche monitoring radar in North Sikkim. Rapid detection is possible with this radar. It can also work in the different weather condition, and the coverage area is the 2 kilometer square around the sensor, right. And the technology here which is used is the microwave pulses to scan and detect the avalanche activities in the surrounding area. And other than the snow avalanches, this radar can also detect landslide, increasing in the utility in hilly terrains, right. So, the effects of avalanches are listed here. So, for example, flash flood can cause disaster in low lying area due to debris from avalanches that accompany them, right. So, it also disrupts the transportation and harms the property, right, and the communication failure at the higher altitude is very common. So, you have seen the different aspects of the avalanches, and this particular slide explains the number of affected people and loss of lives in different country because of the snow avalanches. So, with this I will end this lecture, and then you can refer these references if you want to understand more about the snow avalanches. Thank you very much.